Okay, so it has started recording. So welcome back. Today we are coming to towards the end of the course. After this class, we have two more classes. Maybe I will take one more extra class. We will decide soon. So today we are going to prove. So last class we started with an introductory result in order to prove Dirichlet's unit theorem, and today we will finish the proof. Today we will prove Dirichlet's unit theorem. Okay, so let me start sharing the screen, the slides, and you can just confirm that you can see the slides.
Yes, sir.
Okay, so let's start. So today we will do the unit theorem. We saw the statement in one of the classes. I'll recall again and then continue from there. So let's start. So this is the picture. We are doing slightly more generally what are called S units. So consider a finite subset. So what is MK? MK is the canonical set of absolute values of K, where K is a number field. And S infinity is the Archimedean places. It could be real or complex. So you consider a finite subset S of the canonical set of absolute values and assume that it contains all the infinite places. There could be some finite places. Finite is same as saying non-Archimedean, which is same as saying discrete. So it could contain some finite places also, finite absolute values also, but it certainly contains all the infinite absolute values. So S could be S infinity. When S is equal to S infinity, it is a usual Dirichlet's unit theorem. We are doing it slightly more generally for what are called S units. Okay, so this is the setup. And S unit, this is the definition, is alpha in K star such that its absolute value, Vth absolute value, mod alpha V is 1 and it is an S unit. So where is S coming? This is true for all V outside S. Because S contains all the infinite absolute values, outside S is all finite absolute values. So mod alpha V is 1 is same as saying alpha is a unit in that particular completion. Okay, and if it is true for all V outside S, then it is called an S unit. And if S is S infinity, it's called just a unit. So this is the notation K subscript S. It's a set of S units. And when S is S infinity, these are called the units of K, rather units of OK. Units of, right? If S is S infinity, then mod alpha V is 1 for all the finite places, all the non-Archimedean places. So that will force it to be an algebraic integer because it belongs to, it's a unit in every p-adic completion. So it is a p-adic integer for all p, and therefore it belongs to the intersection of all the p-adic integers, which is a ring of integers. So it's actually a unit of OK. Okay, so let S denote the smallest, denote the cardinality of S, capital S, and we are going to state the theorem now. So let V1 etc. Vs be the absolute values of S. S is a finite set containing S infinity, and consider the map. We are calling it log. It is from S units Ks. So this is all alpha such that mod alpha V is 1 for all V outside S. To the Euclidean S space. S is the cardinality of capital S, and you take Rs, real line power S, Euclidean space. And what is the map? Map is you take an X unit and take these absolute values V1 to Vs. So take mod X1, norm X1, etc. norm Xs. What is norm X? If you recall, norm XV is mod XV power NV. What is NV? You complete at V, Q and V lies above V naught, and you complete Q at V naught, you get Q V naught. You complete K at V, you get K subscript V. That is an extension. That degree, the local degree is called NV, and mod XV power NV is our notation as norm XV. So X going to, you take norm X1, etc. norm Xs, take the log. So this is all these norms are positive, so log makes sense. and it will be a real number, and this is the map. This is a homomorphism. Ks is a group, right? S units will form a group. Product of two units is a unit, and inverse of a unit, inverse of a S unit is a S unit. So it's a group, and this is a group homomorphism. Right hand side is additive, norm is multiplicative, and log makes multiplicative to additive. So this is a group homomorphism, and the image of Ks. So if you take X in this, what can you say about the product of norm x1 up to norm xs? If you take product over all the absolute values, what is the answer? We have the product formula. It is 1. And therefore, the sum of log of the whole product is 1. But outside S, we are anyway assuming norm is 1. So the infinite product is same as a finite product over V in S. So if you take log, that finite product will become sum of logs. So you will get log mod x1 plus log mod x2 plus etc. log mod xs, and that will be log of 1, that is 0. So product formula tells you that the image of Ks is contained in the hyperplane defined by xi1 plus etc. plus xis is 0. So you have the S dimensional Euclidean space, and you have this S minus 1 dimensional hyperplane, xi1 plus etc. plus xis is 0, and the image is contained inside this. And what is the dimension of this space? S minus 1. Therefore, the dimension is, so this follows from the product formula, and therefore the dimension, the image is at most S minus 1 dimensional. Okay, and we are going to show that it is actually equal to S minus 1. So unit theorem, this is the unit theorem. It asserts that log Ks, the image of S units, it's a discrete subgroup of Rs. It's a homomorphism of a homomorphic image of a group. So it's a group. Log Ks is a group. We are going to show that it's a discrete subgroup. In the Euclidean topology, if you take the subspace topology, it is discrete. Every singleton is open. So it's a discrete subgroup of Rs, and the vector space generated by it is exactly equal to this hyperplane. So we know that it is contained in this hyperplane, but we are going to claim that it's a discrete subgroup, and the vector space generated by elements of log Ks is this full image, the full hyperplane. So it is S minus 1 dimensional. This is the content of the unit theorem, originally due to Dirichlet, when S is S infinity. So this gives you a good picture of how the set of units, the group of units, that looks like. So let's start the proof. So let's see that the image is indeed discrete. This is easy. Firstly, the image is discrete as there can only be finitely many elements of log Ks in any bounded region of Rs. This is enough, right? So if you take an open bounded set, if you take a small enough open set, you can assume it's bounded, and that intersection with log Ks, it has only finitely many elements. So you can take a smaller open set so that the intersection will be singleton, showing that singleton is open. That shows that it is discrete. So any bounded region will contain only finitely many elements of log Ks. Why is that? Because if you take x in Ks and if you take log x and assume that it's in a bounded region, if log x lies in a bounded region, then in particular, x lies in a bounded region, and not just x. What is the map log? Log x is log of norm x1, log of norm x2, etc. So norm x1, norm x2, norm x3, all these are bounded. All these are in a bounded region. But if V is Archimedean, then norm x1, norm x2, etc. are just the conjugates. So the conclusion is X is bounded and all its conjugates are also bounded. X is bounded and all its conjugates are also bounded, and therefore what can you say? So absolute values of X and its conjugates must be bounded, and therefore the coefficients of the minimal polynomial of X over Q, they are bounded, because what is coefficients of minimal polynomial? These will be polynomial expressions in X and its conjugates, right? Symmetric polynomials in X and its conjugates. So since X and its conjugates are bounded, all these expressions are bounded. So minimal polynomial, the coefficients of the minimal polynomial are bounded. we would like to say that there are only finitely many such minimal polynomials, but it's over Q. So in a bounded interval, there could be infinitely many Q. But we would like to say in our case, there are only finitely many possibilities. That is because this has beyond the Archimedean things, if there are other places in log x. So suppose there is a discrete V in S, and if you consider norm x V, this is also bounded. You are saying that log x is bounded. So this is also bounded. But what is the meaning of saying norm x V is bounded? Norm x V is bounded says that if you write x as numerator by denominator, the denominator is bounded. Right? Because it's a denominator, in our correct normalization, it will be 1 by norm p power the valuation. So if the denominator is unbounded, the norm will be unbounded. So for norm being bounded, the denominator is bounded, and x is a denominator at that prime is bounded. So a prime which is dividing the denominator can come only to a bounded degree. Okay, so if 2 is an allowed prime in S, then 1 by 2, 1 by 4, 1 by 8, etc. You could have taken 1 by 2 power n as n goes to infinity. But beyond a point you can't take, because then norm will not be bounded. So a prime comes with a bounded degree, and x is an S unit. So outside a finite set, there is no prime dividing the denominator or numerator, in particular the denominator. So because x is an S unit, only finitely many primes are allowed to divide the denominator of x. And because norm is bounded, these primes which divide the denominator also can divide it only to a bounded power. So all said and done, this minimal polynomial, if you consider the minimal polynomial of x, the coefficients are in Q and with bounded denominators. So there are only finitely many such polynomials. So x can satisfy, because of the boundedness of log x, x can satisfy only finitely many irreducible monic irreducible polynomials. So because degree is also bounded, right? Degree is bounded by the degree of k over q. So all this put together, there are only finitely many such polynomials, and hence only finitely many elements of log ks in any bounded region of Rs. So this shows that the image is discrete. Okay, so the image is discrete. Now what do we need to show? We need to show that the vector space generated by log ks, it is S minus 1 dimensional. We know that it is contained in an S minus 1 dimensional hyperplane. We want to see that, say that the vector space, the R vector space generated by log ks is the full hyperplane, S minus 1 dimensional. So we are going to claim one lemma. So last time what did we do? Last time we did some volume computation. We defined the volume of a parallelepiped, and we had the size of an MK divisor, and we said that there are two absolute constants depending only on K, such that the volume of the MK divisor is bounded below and bounded above by the size up to multiplication by these constants. We are going to use that and prove a lemma. This is the lemma. Given one place, fix an absolute. So sometimes I use the word place. PLACE, place for an absolute value. Though Lang doesn't use it maybe. So given V0 in MK, you give me one place, one absolute value V0. Then I am claiming that there is a constant, there is a positive constant CV0, such that for any MK divisor C. So you recall MK divisor? It's a real valued function defined on the set of absolute values satisfying three conditions. One, it is positive. Second, almost always the value is 1. And third, for all discrete places, it is given by mod alpha V for some alpha. So for any MK divisor C, there is a beta, of course, depending on C, such that norm of beta C. So beta is also an MK divisor, right? Beta gives an MK divisor which is mod beta V. And C is an MK divisor, product of two MK divisors is an MK divisor. So you can take norm of beta C. Do you recall what is the definition of norm beta? Norm beta is mod beta power NV. And what is norm of C? Norm of C is CV power NV. C at V, that's a real number, power NV. So the claim is there is a constant CV naught, fix a place, and corresponding to that there is a constant CV naught, such that for any MK divisor there is a beta. Beta of course depends on C, such that a norm of beta C at V is in between 1 and this constant CV naught, and this is true for all V naught equal to V naught. So you can give me a place V naught. Depending on that V naught, there is a constant, such that for all V not equal to V naught, I have this inequalities. So this is a corollary to the result that we proved last time. So let's do it. So last time we showed that there are constants C1 and C2, positive constants depending only on K, such that lambda C. So you recall what is lambda C? Lambda C is the number of points in that set which we call L of C, capital L of C. And what is L of C? Those field elements X such that mod XV is less than or equal to CV. And that number we bound it by the size of K, the volume of K, the volume of C, size of C. So this we showed last time for any MK divisor C, and now we are going to take C naught to be, so if it's an Archimedean place, you take C naught to be 1, and if it's a non-Archimedean place associated to that, there's a prime ideal, and you take the norm of that prime ideal. So that's a number, right? That's a prime power. P power, the residue cardinality there. Now let C prime be an MK divisor. I'm going to choose C prime. This is mostly C. At all the places it is C except at one place. It might differ from C only at V naught. So C prime, I'm going to define a new MK divisor, C prime. What is the value of C prime? So C prime is a function on absolute value. So if V is an absolute value, I have to define what is C prime at V. And my definition is C is given to us. My definition of C prime is C prime at V is same as C at V. Whenever V not equal to V naught, it is same as C at V. At V naught, I need to define it slightly differently, and I am going to define it so that these inequalities are satisfied. What is C1? C1 is a constant in this lemma. C1 is a constant in this lemma, in this result that we proved last time, and C0 is this constant, and I am going to define this C divisor C prime at all V other than V0, it is CV. So what is the size of C prime? Size of C prime is product over all absolute values norm of C prime V. But norm of CV you already know because C is given to you, and at C prime at V naught, I will change it. I will change in such a way that this inequality is true. You agree with this? So C at V is given to me at all V not equal to V naught. Now at V naught, you define C prime so that this inequality is true. So product of C prime at V not equal to V naught, you already know. These constants C1 and C0 by C1 you already know. So define C prime at V0 so that it is in between this. So you may have choices. Define whichever way. You are only interested in this inequality being satisfied. This is okay, right? Because if V is Archimedean, then C prime V you can define as any real number. And if V is non-Archimedean, then C prime at V0 should be a power of norm P naught. If P naught is the corresponding thing, it should be discrete valuation. So it should be a power of positive or negative power of norm P naught. But C naught involves a norm P naught, so that also you can adjust and define. So either way you can define this, whether V naught is Archimedean or non-Archimedean. So this is important. And now we are saying that if you define CV naught to be this constant C naught by C1, then this is satisfied. Okay, so we want to prove that there is a beta such that this is true, and that's what we are going to claim now by taking CV0 to be this constant. And how is that? Because we know that lambda at C prime, we have proved last time that for any MK divisor C, lambda C is bigger than C1 times its size. So lambda at C prime is bigger than C1 times size of C prime. So lambda of C prime is bigger than C1 times size of C prime. And the C1 times size of C prime from here, C1 times size of C prime is bigger than or equal to 1. So what you know is lambda of C prime is strictly bigger than 1. But what is lambda C prime? Lambda C prime is a cardinality of L of C prime. So lambda C prime is strictly bigger than 1. Therefore, L of C prime has at least 2 elements. At least 2 elements. Of course, 0 is there. So one element is 0. So there is at least one non-zero element because there are at least 2 elements. So there is at least one non-zero element. So there exists alpha non-zero such that alpha belongs to LC prime. By definition, that means mod alpha V is less than or equal to C prime V for all V in NK. This is the definition of LC prime. LC prime consists of all alpha such that mod alpha V less than or equal to C prime V for all V. And you can take power NV. So mod alpha V power NV is norm alpha V and C prime V power NV is norm C prime V. So therefore norm alpha V is less than or equal to norm C prime V for all V in MK. Such an alpha we know. We got because of our result of last class. Okay. Now what do you need to show? You need to show that there exists a beta such that beta times C is bigger than or equal to 1. And we are almost there because we have shown that there exists alpha such that norm alpha less than or equal to norm C prime. So if you define beta to be 1 by alpha, then beta C prime, right, 1 by alpha times C prime is bigger than or equal to 1. So define beta to be 1 by alpha. So you get 1 less than or equal to norm beta C prime V. And where do you get this? You get this for all V in MK. Okay, now I claim that this is enough. We have proved the first inequality. We wanted to show that 1 less than or equal to norm beta CV for all V not equal to V naught. And what we have just shown is 1 less than or equal to norm beta C prime for all V. Why does this follow? We have shown that 1 less than or equal to beta times C prime V for all V. Therefore, this follows because for V not equal to V naught, C and C prime are same. C prime is defined so that C prime differs from C only at V naught. So, therefore, the first inequality follows. As C prime and C differ only at V naught, we get 1 less than or equal to, here I am replacing C prime by C, 1 less than or equal to norm of beta CV for all V not equal to V naught. Agree? And one remark which is useful when we proceed, which is that if you take any discrete V, then what do you know about norm beta at V? Norm, whatever element you take, alpha or beta, alpha, norm alpha at V, if so V corresponds to, V is discrete, V corresponds to a prime ideal. Now that prime ideal may divide either the numerator or denominator of alpha, but for almost all such primes, it will not divide the numerator or denominator, right? Numerator will have only finitely many prime factors, denominator will have only finitely many prime ideals. So all but finitely many prime ideals will not divide the denominator or numerator of alpha. In other words, norm alpha V is equal to 1 for almost all V, almost all discrete V. And this C prime, because it is an MK divisor, for discrete V it is given by some element, let us say alpha prime. And for that alpha prime also, mod alpha prime V is 1 for almost all V. So the conclusion is that this inequality which we have in the previous slide, and then I define beta to be 1 by alpha, with alpha was this. This inequality is actually an equality for almost all V. Almost all discrete V, the inequality is actually an equality. Do you see this? Because C prime is given by an alpha prime and norm of C prime is nothing but norm of alpha prime, and norm of alpha prime is 1 for almost all V. And norm of alpha is also 1 for almost all V. So both of them are 1 for almost all V. Therefore, this is an equality. In other words, this inequality is also an equality for almost all V. This inequality that we are proving for all V not equal to V naught is actually an equality. Actually, it is an equality for almost all discrete V. This we will have to use soon. Okay. Now we have the other inequality. We had an inequality on the left hand side and an inequality on the right hand side. And for the right hand side inequality, you have to show that this is less than or equal to something, CV naught. And for that you do this. So beta C prime at V is nothing but beta C prime at K divided by beta C prime at all W not equal to V, because this is product over all the places, all the absolute values. So this is by definition this, and this is less than or equal to beta C prime K because each of this is bigger than or equal to 1. All these things are bigger than or equal to 1. So you are dividing by something which is bigger than 1. Therefore, this is less than or equal to this. As all these are bigger than or equal to 1, which was the first part that we proved. First part inequality. Okay. But now if you consider this, beta C prime, the size of it, the K size of it, that is same as C prime, the K size of it, because of product formula. If you multiply by any field element, it doesn't matter. Its product is 1. Product over all places, norm beta is 1 because of the product formula. So this is norm C prime K, but we chose C prime so that an inequality is true. C prime is less than or equal to C naught by C1. That was our choice of C prime. Therefore, this is C naught by C1, which is what we call CV naught. So the right hand side is also shown. So therefore you get 1 less than or equal to this, less than or equal to CV naught for all V naught equal to V naught. But remember, this is an equality for almost all V. It's actually an equality for almost all V. Okay, this is the first lemma. This is the claim that we wanted, and this we are going to crucially use. So next we show that given an index, right? Your cardinality of your set S is small s, and you have the absolute values there, which we call V1, V2, etc. Vs. All the Archimedean absolute values are there. Possibly some non-Archimedean absolute values are there. I don't care. So given an I am going to make this claim. There exists a vector psi1 etc. psi s in log ks with the property that psi I, so these are all real numbers, right? This is contained in R power s. These are all real numbers. It's an S tuple of real numbers. So given an I, I'm going to claim that there is a tuple in log ks with the ith coordinate positive and all other coordinates negative. This is the crucial claim that we are making. And this claim will prove Dirichlet's unit theorem. So given an I from your S, there is an element in the image, there is a tuple in the image, so that the ith coordinate is positive and all other coordinates are negative. So in order to show this, we need to show that given V naught in S, right, I corresponds to some V naught, given V naught in S, there exists U in Ks, so that log U has one component corresponding to V naught positive and all other components negative. But what is ith component? Ith component is log of mod norm U V naught. Ith component, if I corresponds to V naught, you are taking norm U V naught and you are taking log. So log norm U V naught. So if, and all other places will be log norm U V. So if you want all other things to be negative and ith place to be positive, what is the claim on norm U? Claim is that norm U V naught is very large, so that when you take log it is positive, and all other places norm U V is very small, so that when you take log it is negative, right? Less than 1 will give you negative, greater than 1 is positive. So the claim is that there exists an S unit U such that norm U at V naught is very large and norm U at V is very small for all other V in S minus V naught corresponding to J naught equal to I. Okay, this is the claim. And we are going to use this lemma in order to show this. Okay, I hope the statement is clear. So let's prove this. So I want to show that there is an S unit U. Given U give me a absolute value V naught. Correspondingly, I will construct an S unit U such that norm U V naught is very large and norm U V is very small for all the other absolute values in F. So again, we are going to employ MK divisors. So let C be an MK divisor, and we know that there exists a beta such that for almost all V, 1 is equal to beta C norm V, right? When I proved the lemma 1 less than or equal to norm beta C, I also said that for almost all V, it's an equality. So for almost all V, it's an equality. Therefore, there is a finite set S prime such that 1 equal to norm beta C for all V outside S prime, right? Almost all. That means except for finitely many V, this equality is true. That means there is a set S prime such that outside S prime, this is true. Now, without loss of generality, you can assume that S prime contains S. Why is it without loss of generality? What you do is you got such an S prime, and if it doesn't contain S, you adjoin S. You take S prime union S. You enlarge S prime and assume that S prime contains S. So this assumption is okay. And now you consider a collection of MK divisors C. This collection has a certain property. You're not interested in all MK divisors, but see, your final result has no MK divisor. MK divisor is a tool that you're using in order to construct such a vector. And norm u v naught is large and norm u v for rest of v is small. In order to construct such a S unit, you are using this tool of MK divisor. So consider the collection of MK divisors C such that these two things are true. CV is bigger, so you know that CV is positive for all V, but you take only those C where CV is actually bigger than 1 for all V and CV equal to 1 for all V outside S. You know that CV is 1 for almost all the time, but inside S it may not be, outside S maybe there are C such that outside S it's not always 1, but you consider only those C. So CV is bigger than or equal to 1 for all V and equal to 1 for all V outside S. For this collection of C, if you apply your lemma, there is a beta, of course, depending on C, such that you get 1 equal to norm beta C, right? V outside S prime, you know that 1 equal to norm beta C. So this part is, we already know, that is the definition of S prime. But this is equal to norm beta V because V outside S, if you take V outside S prime, then that V is outside S because of this containment. And outside that CV is 1. So if C, what is norm CV? Norm CV is CV power NV. So if CV is 1, norm C is 1. So norm beta C is nothing but norm beta V outside S prime. And you have the lemma. Lemma is that 1 less than or equal to norm beta C less than or equal to CV naught for all V not equal to V naught. This is true for all C. So in particular for such C. So depending on C, you have got a beta. So you consider the collection of all such C, and for each such C, you get a beta. Okay, so you have got a collection of betas. That collection of betas. So one more remark is that norm beta less than or equal to norm beta CV less than or equal to CV naught for V not equal to V naught. Why is that? That is because norm C is bigger than or equal to 1. CV is bigger than or equal to 1, you are assuming. Therefore, norm C is bigger than or equal to 1. So norm beta is less than or equal to norm beta C because norm C is bigger than or equal to 1. So norm beta is less than or equal to CV naught, which means that for discrete V, there are only finitely many choices for norm beta V, right? Norm beta V is bounded by an absolute constant. So if norm beta V is bounded and if V is discrete, norm beta V is 1 by NP power something. But 1 by NP is a positive number and the powers are integers. So because it is bounded, you have only finitely many choices. It is bounded above and it is also bounded below because norm beta V is I want to say that there are only finitely many choices for norm beta V. Why is Why are there only finitely many such things? Because it is bounded above. Therefore, 1 by norm p power something is bounded above. Therefore, so 1 by np is something less than 1, and a high power of that is bounded above. So that means the power cannot be very negative. It cannot be minus of a large number, because if it is minus of a large number, then 1 by np power that would cross the CV naught. So there is some bound there, and that's not enough for me. I'm saying only finitely many choices are there for norm beta v, and that is because of this. See, norm beta v is 1 for all v outside S prime. So v outside S prime, it is also equal to 1. So v outside S prime, norm beta v is 1. So only for v in S prime, only for finitely many v can divide the denominator. So I need to include this also. From both those conditions together, there are only finitely many choices for norm beta v. This is important for the next step. Let B be the set of all such beta. What is the meaning of all such beta? You consider the collection of all such C, and for each C you are getting a beta. You consider the collection of all such beta. And now we are going to do the following. B be the set of all such beta, and you consider the map B to this Euclidean space where you have capital S prime containing capital S, small s is the cardinality of S, and S prime is the cardinality of S prime. So from B to this Euclidean space of dimension S prime minus S, you send beta to the tuple norm beta V, where V belongs to S prime minus S. Okay? And the image of this is finite. Why is that? Because we have concluded here that there are only finitely many choices for norm beta v. So there are only finitely many choices for each of the norm beta v, and this is also a finite set. Therefore, the image of this map is finite. Image is finite. And this is good because now, because the image is finite, let us enumerate representatives. So let beta 1, etc., beta m be representatives in B for the elements in this image. So image is finite. So suppose it has cardinality m, and you consider beta 1, etc., beta m be representatives of this. That means beta 1 and so all the elements in B will be beta 1 times an S unit, beta 2 times an S unit, etc., beta m times an S unit. Because S unit meaning norm V is 1 for V outside S. So V in S prime minus S. So it will be multiple. So anything else will be one of this times an S unit. So consider this thing, and extra pause here, and define B to be the minimum among all these things. So take V in S prime minus S and J varying from 1 to M, beta 1, etc., beta M. Take the norm of beta J, the absolute value V, take this B, and B is of course positive because it's a finite set of positive numbers, and you're taking the minimum. And for all beta in B, there is an S unit U beta and some J such that beta is U beta Bj. You agree? Because beta 1, etc., beta m are the representatives. Anything else is an S unit times that. So given a beta in B, there is an S unit U beta such that beta is U beta times beta J, there is some J. And we have shown this, that 1 less than or equal to norm beta C less than or equal to CV naught for V naught equal to V naught. This was our lemma. And from this lemma, it follows that for any C in our collection, norm C can be bounded. Norm C is less than or equal to CV naught by norm beta. But norm beta is same as norm beta J, and norm beta J, the minimum is B. So in the denominator, you can replace that. Depending on C, you have an S unit such that norm of UC at V is less than or equal to CV naught by B. Right? You see this? Because norm of C, beta is a unit times beta J. And unit times C you put here, and beta J comes below, and beta J can be replaced by this B because it's a minimum. So in the denominator you can replace that because it's less than or equal to. So you get this for all V not equal to V naught. So agree? So you get this, and now you choose a C. You have a collection of C. So you choose C such that CV is very large. It's up to you, right? I mean, MK divisor you can define as you like. So you choose C such that CV is very large for all V in S. It's a finite set S, and for all these finitely many elements V, CV you choose to be very, very large. Take such a C. Then what can you conclude? CV naught by B is an absolute constant. B is also an absolute constant. So this is a constant. So if norm CV is very large, then you conclude that norm U has to be, and this is true for this is true for all V not equal to V naught. So, and you have chosen CV to be very large for V in S. Therefore, for V not equal to V naught, what is the conclusion from here? Norm UC is bounded and norm C is very large. So norm U has to be very, very small. Norm U at V has to be very, very small for V not equal to V naught. Otherwise, you will not get this inequality. But if norm U V is very small for all V not equal to V naught, then norm U at V naught has to be very large. Why? Because of the product formula. The whole product is 1. Therefore, if all of this is very small, then at V naught it has to be very large by the product formula. This is what we wanted to show. We wanted to show that there is a tuple so that at the ith place it's positive and at all other places it's negative. So that's equivalent to showing this. All right, so this was our first claim. So here also there's an extra pause. So 2 extra pauses. So next we claim that, right, what do we want to show? We have already shown that the image is discrete, and we want to show that the image generates a vector space of dimension s minus 1. For that we are going to show that any s minus 1 vectors, if you take from this collection. So what is the property of this collection? Psi 1 etc. psi s in log ks. One of them is positive and all the others are negative. For some I, psi I is positive and all j not equal to I, psi j is negative. That I might vary. If you take collection of such tuples and if you take any s minus 1 vectors from this collection, we are going to show that they are linearly independent. And in the last slide, we have shown that such vectors exist. Given I, there is a vector such that ith element is positive and all other elements are negative. So if we make this claim, this proves the Dirichlet unit theorem. Because then we would have proved that there are such collections and any s minus 1 of those is linearly independent and it's contained in an s minus 1 dimensional hyperplane. Therefore, the vector space generated by log ks is the full hyperplane. Okay, so this is what we have to show. This is elementary linear algebra. It's just, showing linear independence from scratch. So let's denote xi to be the vector psi i1 etc. psi is with the property that psi ii is positive and psi ij is negative for j not equal to I. And we are going to show that x1 etc. xs minus 1 is linearly independent. This set is linearly independent. And we are going to show by you consider the s minus 1 by s matrix. By putting all these together, you will get s minus 1 by s matrix, x1 etc. xs minus 1. And you are going to show that the first s minus 1 columns are linearly independent. That's enough, right? If the first s minus 1 columns of this matrix are linearly independent, then the s minus 1 rows are also linearly independent. So this is from definition. So if the columns are called y1 etc. ys, then suppose a linear combination is 0, you want to show that the coefficients are 0. So if columns are y1 etc. ys, then you have s minus 1 by s, right? So columns are y1 etc. ys, and if you have you're going to show that the first s minus 1 columns are linearly independent. So suppose you have a linear combination a1 y1 plus etc. a s minus 1 y s minus 1 is 0. What will be the very, so you will get s minus 1 many equations, right? A column vector, you have got a linear combination, but column vector, you know, the first column vector is psi 1 1, psi 2 1, etc. Second column is psi 1 2, psi 2 2, etc. So you got s minus 1 many linear equations. Just take one of those equations. Just take the first one. In particular, you will get, applied to the first one, you will get a1 psi 1 1 plus a2 psi 1 2 plus etc. plus a s minus 1 psi 1 s minus 1 is 0. And you have to show that all the ai's are 0. So suppose all the ai's are not 0, you will get a contradiction. AI is a real number. Without loss of generality, you can assume that A1 is positive and A1 is the biggest. By interchanging columns, you can assume that A1 is bigger than or equal to AJ for all J and A1 is positive. Now what you do is, since psi 1J is negative for all J not equal to 1, you can add A1 minus AJ psi 1J, A1 minus AJ psi 1J for all J not equal to 1, you can add to this. What do you know about the sign of this? A1 minus AJ is positive and psi 1J is negative, therefore this is negative. So adding negative numbers meaning subtracting. So by adding all this, you will get 0 is bigger than or equal to, because you are subtracting a positive quantity. You are replacing A2 by A1, AS minus 1 by A1, everything by A1. That is same as adding A1 minus AJ times this, which is a negative number. So therefore this is an inequality. And here A1 is common. So you got A1 times this, but A1 is positive. So the conclusion is psi 1 1 plus psi 1 2 plus etc. This is negative. But this is a contradiction. This is not correct. Why is that? This is a contradiction because you know that the full tuple is in that hyperplane. Image is in that hyperplane because of the product formula. And therefore this sum is minus of psi 1s, but psi 1s is negative, therefore minus of psi 1s is positive. So you know that this sum is positive, but you got that this sum is negative. That's a contradiction, and the contradiction is because you assume that not all ai's are 0, therefore all ai's are 0, and that's what you wanted to show, linear independence. Okay, so this proves the Dirichlet unit theorem. You have given this map log from S units to RS, and you have shown that the image is discrete, and you have shown that the vector space generated by the image log Ks is an S minus 1 dimensional space. And another observation which is proved in Lang, or maybe you already know this, is that a discrete subgroup of a Euclidean space is automatically free abelian. Okay, so this you can check Lang if you want to see a proof. So it's automatically free abelian. And one more observation is, what is the kernel of this map? So this is the map x going to log mod x1, log mod x2, etc., log mod xs. Just look at the Archimedean places and kernel of this. So the image is 0 0 0 0 etc., right? So that means log mod x1 is 0, log mod x2 is 0, etc. That means mod x1 is 1, mod x2 is 1, mod x3 is 1. So all the mod x is 1. Just looking at the Archimedean places, what can you conclude about x? X and all its conjugates have absolute value 1. If a complex number has the property that all its conjugates have absolute value 1, then what can you say about that complex number? Yeah, not any complex number. It is coming from K. It is coming from this number field. So you have an element from K, a finite extension of Q, and you know that all its conjugates, all its Galois conjugates have absolute value 1. So what can it be? Yeah.
If we can say that the constant term in the polynomial will be 1 or minus 1.
Yeah, yeah. And just try to take a guess. Can you think of elements Can you give me examples of elements all whose conjugates are 1? Okay, take from Q itself. Suppose your field is Q. What are the elements or conjugates? So conjugate doesn't mean anything here because it is Q. So what are the elements of absolute value 1 from
Plus
Q?
1 minus 1.
Plus 1 minus 1, right? Now suppose you take a quadratic extension.
Okay. I is also possible.
Yeah, if it is Qi, then I is possible. If it is Q root 2, then only 1 or minus 1.
Yes.
Otherwise, you have I or minus I. So more generally, what do you think?
Roots of unity.
Roots of unity. So you can show that only roots of unity will have this property. So the kernel consists of roots of unity. Okay. So kernel of this. So what you have proved finally is that you have this homomorphism. Image is a free abelian group, assuming this result. Image is free abelian. What is the rank of that free abelian group? S minus 1, right? We proved Dirichlet's unit theorem. The vector space generated by that is S minus 1 dimensional. So rank of that free abelian group is S minus 1. And there's a kernel which is roots of unity. So the unit group is fully understood. It is a finitely generated abelian group. So what finally we have realized is the group of units is a finitely generated abelian group. Its torsion is precisely roots of unity. And the rank is S minus 1, where S is a cardinality of S. In particular, if S is S infinity, then these are exactly units of your ring of integers. So the conclusion is units of your ring of integers is free abelian, not free abelian, finitely generated. And a finitely generated group has the notion of a rank, how many copies of Z are there, and that is equal to R1 plus R2 minus 1. R1 is the number of real embeddings and R2 is the number of complex embeddings. Because that is how we constructed S. S consisted of, yeah, so maybe my notation was slightly wrong when I meant S consisted of S infinity. Yeah, the absolute values corresponding to that, right? So complex absolute values come in pairs. A plus bi going to A plus bi and A plus bi going to A minus bi. Absolute values are the same for those two embeddings. So if you have 6 complex embeddings, only 3 things are coming in S, half the number of complex embeddings. So if R1 is the number of real embeddings and 2R2 is the number of complex embeddings, then the unit group has rank. It's finitely generated of rank R1 plus R2 minus 1 because it is S minus 1. Okay, this is what we have proved. Let's stop here. And now I have 2 more lectures. I will say something about Minkowski's bound. I don't know how much I can prove. I'll try to prove as much as possible, but certainly we will state the result. And finiteness of class number without getting into Minkowski's bound, we quickly went through in Lang's book one of these extra classes. By stating Minkowski's bound, that particular result, I don't need to state the usual finiteness of class number thing because this is much better than that. And then we can stop. Yes, so good. So we are covering whatever we wanted to cover. So I will stop the recording. I will stop the recording and